So this course is mathematics of generative modeling. Okay. So let's say this is a new course. Let's say we call it MGM. Okay, in short. And if I have to kind of write it in one word what this course is about, then maybe like it may not be something standard to say, but maybe I will do something like this. Okay, and here is the distribution that I want, and this is some model that I have. Okay, and it could be something else also. It's a uniform. Okay, what are these? These are distributions. Okay, probability distributions. We will read about probability as well. This is probability distribution. This is probability distribution. Standard normal. Everything known. Parameter. There is no like variable mu or sigma here. It's known. Standard normal known. I can sample from this. Okay, so I can sample. Okay, from this. It will be some vector. Okay, so and then it will go through certain model. Okay, this model again will be some hypothesis. Okay, hypothesis class or function or whatever you want to say. Okay, because this model can essentially be seen as some kind of function that takes these samples, okay, and it produces something which is interesting in real world. Okay, so it could be like cat image, dog image, or whatever, but of course it depends on what I'm training for. Okay, so am I training for all the cat images, then it will learn to produce cat images. But what is interesting in generative model is that it generates. So this is the keyword here. It does not produce the same thing on which it has been trained on. It generates. So as someone said, so let us say one of the generative model, like there are like quite a few of them, and of course in this course we will see like all of them. It's like even those who are not that good, we will see even those. Okay, those who are not, I mean, in a unified way we want to see everything. Okay, but focus is on all the methods for generative model, because you never know when things switch. Okay, so there are probabilistic based idea, there are non-probabilistic, like let's say implicit ideas, explicit ideas. Explicit ideas explicitly give me the probability distribution, and then implicit ideas they don't give me, I go via some latent space and so on. Okay, if this doesn't make sense, it's fine. I'm just giving a little bit of overview. And okay, so the whole course is about the generative modeling, and in some sense you can say this whole course is about how well I know, given a probability distribution, how well I know to transform into something new. Okay. So there could be very simple things from probability, like given a uniform distribution, can you generate some other, okay, like whatever. So let's say I would look into, I mean, if you have done probability course, then you may be given some random variable, and then we will you will be asked, okay, what is the random variable x? Give me the PDF of x square. Okay. So these are also some form of transformation. So here I'm going from I'm going to generate a new PDF. Okay. So this is like the basic thing that we will see, but then here we need a lot more complicated model, because yeah, I mean these are not really even known distributions. Okay, but what we sample is obviously should be known, so that I can generate new random samples and then I can keep getting something new. Okay, so what I almost forgot what I was going to say, so now I come back. Okay, so yeah, so what there is a saying that so I work on GAN basically. We have like a couple of papers on that. So this is one of the generative model. It's called generative adversarial networks. Okay, generative adversarial networks. Okay, The problem here is formulated as a game theory problem. It's a min max. Okay, so it's like a game, two-player game. Okay, obviously we will see a lot more about that, but yeah, saying too many things may not be good right now. So, but two-player means essentially it's an optimization problem, min max type. Okay, not just min, but min max. Okay. Okay, something like that. Okay, min over x, max over y. Okay, so around 2016. Okay, good fellow. Okay, proposed yeah, and like similar ideas were even before that, but we don't want to get into conflicts. But yes, I mean, this was one of the prominent models that came into prominence in 2016. Okay, and yeah, so with this GAN, we could essentially, what goes here, I don't want to say right now, but essentially some kind of training goes on. Okay, and then later it starts producing something very interesting. Okay, it depends what you train on. Okay, whether it's image, okay, even now you can do video, okay, text, and so on. Okay, so what did GAN do, right? GANs gave machine learning. Okay, these are not my quotes. Okay, these are quotes by some other guys. Like, so GANs gave machine learning imagination. What did you do so far in machine learning? You did classification. Okay, so you have some image of a cat, okay, written as a vector of pixels. Okay, and then you could say whether it's a cat or not. Text data encoded in word to word or character to character representation, or whatever encoding you want to do for your data, and then you can say, okay, this text is about something. Okay, maybe about sentiment or whatever. Okay, so you are doing classifications, you are doing regressions, and so on. Okay, so you are essentially trying to do the prediction in general. Okay, a classification or regression problem. What generative model is doing, it's imagining things for you. Okay, so that's why we say GANs gave machine learning imagination. Now this creates whole set of applications, right? And good thing about imagination, that imagination has no boundary. Okay, so sometimes people say, okay, imagination may be the most difficult, but then it also means, imagination means that you have less, I mean, even if you make error, that will even be seen as a kind of a creative thinking. If an artist paints something and if the artist makes some other stroke, maybe it will be seen as an imagination. So it may not be that difficult. Okay, so a few years ago, people were thinking, oh, okay, I mean, machine learning, what can it do? Okay, but now it's creating very good art. Okay, so imagination as such may not be very, very difficult in some sense. Okay, so of course many things goes into model and what kind of imagination or models will learn and whatever, that's another story. But apparently it seems like imagination is not that hard in some sense. Like, okay, yeah, I'm saying this with all seriousness. Okay, so classification problem, regression problem, imagination problem is equally looking very exciting. Okay, because it is indeed creating very nice art. Okay, creative videos, text. Now, so let me give you the little bit of developments in this area, and you can already search these. So let us start with the very latest one, right? So we have something called ChatGPT. Okay, so how many of you have tried ChatGPT by now? Okay, it's like almost everyone. Okay, so what have you tried for? Right, what did you do with this? Does it generate images? Not yet, right? I mean, yeah, it may create animations for you, right? So you can say that, okay, create. So I tried this. Okay, create HTML5 animation of a circle rolling over. Okay, so I can write some, so it may not like create as such, but it can create codes for you. I did also for LaTeX, because as a researcher I work a lot with LaTeX, and then there I say, okay, create figure, LaTeX figure. Okay, so you have to write the LaTeX figure for sigmoid function. Okay, so feel free to use these things in your assignments in other courses. Okay, so but anyway, I think it should be legal enough. Okay, as long as you cite that, okay, I'm using this, why should not, right? Whatever comes to us that can be used, why not? Okay, of course you should understand what is a sigmoid function and so on, but if I have to draw a figure, why should I go into those packages like PGF, so it will open up PGF and so on. So there is a package called PGF for drawing figures basically. Okay, it's like inbuilt, like in LaTeX it can draw figures. Okay, so it can do a lot of work like this. Okay, and it's not like it memorized, like it can generate also. If I have some certain demand, okay, by sigmoid with something else also, okay, it will put the code there. I will just copy paste and put it in my LaTeX editor, compile it, and it's okay, but not always okay, but sometimes it fails, but then at least I have a template that I can modify and still work with. Okay, obviously it can solve a lot of maths problems. Okay, so you can try. I tried solving some maximum likelihood. One guy, yeah, this Vamsi. So we were playing around a little bit with maximum likelihood estimates, like 5 red balls, 3 blue balls. Take samples and then estimate how many red balls are there. It does some mistakes. Okay, so we found out, but then it learns. That's remarkable. Okay, so we said, oh, you did some mistake somewhere, please correct, and they say, okay, yeah, I did some mistake, let me go and correct. So it's remarkable. So what I'm saying is, my personal view, intelligence seems to be overrated, especially the imagination. I'm saying this I'm even recorded. So, but it seems to me, my personal opinion, intelligence seems to be over. Why? I will prove also a little bit more. Okay, but again, I'm saying, like, if someone is working on Riemann hypothesis, maybe not. Riemann hypothesis needs a lot more intelligence, but who knows? Who knows where things are going, right? So another thing to support my claim is, let's say, coding competitions, like coding Olympiad. Okay, coding Olympiad, which are very difficult. To do very well in coding Olympiad, you also have to be very good in maths, because many problems are essentially formulated as maths, and then you know what to do with the algorithm, right? The first step is often maths, right? So coding, I mean, not the usual maths, the discrete maths, okay, like graph and so on, right? So, but sometimes also optimization and so on. So it depends, right? So coding competitions, right? Okay, so what is that? So Google, I'm not sure if I remember correctly, Google code or something. Okay, Google code, I guess. Yeah, I have to double check. Okay. So what it does is, it's within 50% of the top coders that goes into coding Olympiad. 50%. It's within. So this is a machine learning model. Okay, I'm not saying it's generative right now, but what I'm saying is, like, in general about intelligence and how much overrated it may be. Okay, overrated in the sense, like, we say, okay, machines can never do this, can never do that. Okay, but quite a lot of things machines can do right now. Okay, so it's within top 50% of coders. Now remember, these coders are the top coders of the world who goes into Olympiad. They are the top. So it's like, it's better than half of the best of the coders you have in the world. Okay, it's better than half of the best of the coders in the world in solving new problems. I'm not even saying like it memorized something, right? Solving new problems. That's incredible. I mean, if you are someone who are still thinking that things are not, I mean, machines can't do many things, worry right now. Okay, this is the real time to worry. Okay, because it can do many things. It's just the GPT-1 came like 2-3 years ago. GPT-2, GPT-3, and this is the recent one. It's based on GPT-3 basically. GPT-4 is about to come. Okay, if I remember correctly. This already does a lot of things. There are separate works going on. Okay, that can already do this. There is another work going on where maths problems can be solved, Olympiad problems. Okay, there also it's among like top 50 or something like that. There also. Okay, and Olympiad problems in maths are very difficult. Okay? They are new problems and very difficult. So incredible. Okay, so if we focus on generative modeling, this is based on generative modeling, and there is something called DALI that's more image based. Okay, so this is more text based, but as I said, some animations, LaTeX figure can be computed from here. Okay, there are like variants of this 2, 3. I don't care, but all these are OpenAI. So you can just type OpenAI, and then you will see some tab on DALI, some tab on this, and you try that. Okay. So here it generates images. Okay. So this guy and this guy is pretty much part of our topics. Okay, so here you write some text. Okay, so you say that cat making chapatis. Okay, so it will generate an image of a cat making chapati, and it looks realistic. Okay, I mean, for us it doesn't look realistic, but if you see the figure, it looks like cat is indeed making some chapati or something like that. So it can imagine. That's what I'm saying. Like, it may not have seen, but it understands that okay, there is a cat and how someone is supposed to make chapatis. Okay, so it kind of imagines and creates new images, and then okay, you can build on this and do many things. So this is also part of generative modeling, because it's generating new images and it's generating also text. Someday all this will be combined, and most of us will be useless. Okay, because this guy can start teaching. It actually explains what it's doing. Okay, it's just a matter of time that it might replace teachers, especially the secondary teachers and so on. Okay, this can replace coders. This already can replace 70 to 80% of the coders, because it does write codes also. Okay, and not just that, it writes new codes also. Okay, so not even memorize. Okay, so but as I said, not perfect also. But things are in line. I mean, things are. If you are ignorant, then okay, it's your problem. Okay, and it's a matter of time. So and then there is Google, Copilot or something, right? So there are many things anyway. So last 2 years have been quite remarkable in generative modeling. Okay. Okay. So within generative modeling, so if you look into the ideas, algorithms, then things keep changing, sometimes back and forth. Okay, there are like very similar ideas, but then something takes over, and then you go back to something that you started with. So there are a bunch of ideas here itself. Okay, so we have few things like GAN. So far still now GAN is still popular because of like faster training and so on. So GANs are still useful, and then latest is diffusion model. Diffusion models are mostly, as I said, like probabilistic ideas. So we have to be very good in kind of understanding probability, some amount of random process. So this is the whole idea behind this course, to understand these things very well. Okay, and then some of the old ones are like VAEs and so on. Okay, and within this we have to study things like normalizing flows and stuff like that. Okay, so but we want to study these things in a very structured way. Okay, in a way that we understand very clearly which method differs from what. Okay, in very precise detail and so on. Okay, but then if we have to do precision, then we have to use all the machinery that goes with maths and so on. Okay, so ideally, like ideal scenario, there will be some let's say some complicated expressions, but you cannot in general work with, so you will always do some approximations. Okay, So to learn how to do approximations, you need a little bit of maths. Okay, I will apply some bound. Okay, but then I will apply some inequality. Okay, so do I know about that? Why did I apply that? Okay, when I should apply such things, right? If I use Hansen's inequality, why did I apply Hansen's inequality? Okay, so we will do a lot more about why and how. Okay, and many of you are smart enough to know the practical algorithm, write Python code. Okay, many of you I know are good in that. So that you can do as an assignment or whatever in this course, but that's not my focus as such. Of course, algorithm will be written down, and this is the full algorithm, so on. But that's not the only thing we are supposed to do. We kind of want to get into deeper, like how these ideas were developed in the paper itself. Okay, what were the details? Okay, so so this course will be about that. So as I said, I should not tell too much about these things. This you can go home and like your room and then just do some Google search and see what generative modelings are doing these days. Okay, so without wasting too much time, I will start with some background on probability. Okay, just to recall, like many of you may know already, but rather than distracting too much already, let us get straight away into things that matters. Okay, so let us recall probability. Okay, I don't plan to take like tutorials every time, because as I said, this is a new course and I don't have like too many resources right now. So most of the things will be done in the class. So I'm not expecting that I will go to tutorial and things like that. Anything that is needed will be in the class. Okay, so let us do a quick recall of review of probability. So review of probability and statistics. Okay, so probability as such, if we focus only on probability right now, so probability as such starts with some amount of some experiments. Okay, so we have some experiments. So for instance, so for example, experiment could be toss a coin, and then we have so often these experiments are random. Okay, so random in the sense that the outcome is not known. Okay, so there is a bit of uncertainty. If I toss a coin, I don't know deterministically, hence random. Okay, so I don't know the outcome here. So it's a random experiment. Usually we deal with random experiments, and then there is a possible set of outcomes. Okay, so in this case we call this sample space. So sample space, in this case, all possible outcomes here could be head or tail. Okay, we don't expect the coin to be like the, what is that movie, no, where it falls like that, a Sole movie, right? So in Sole, if you remember, the coin is just like this. Okay, on this is like it falls like that. Okay, neither head nor tail. So we are ignoring those facts. Okay, so we say, okay, let's say there will be certainly two outcomes, and these are the only two outcomes. Okay, so we have a sample space, and these are called outcomes of experiment. Obviously, when I do one, then not both is possible. So one of the outcomes is possible, right? If I do an experiment, and sample space is like collect all those. Okay, so if I roll a die, then it's a six-sided die. Okay, so in this case, the outcomes for me are the numbers on the die on the top. Okay, so then I have like 1, it could be 1, 2, 3, 4, 5, 6. This is also a random experiment because I don't know. So if I play Ludo, I don't know when I get 6 or 1 or 2. So it's a random experiment, and this is the sample space, basically all collection, all possible outcomes. Okay, and we can have sample space which have kind of like pair of outcomes. So for instance, I can also roll a 3 coins, right, or toss 3 coins at a time. So in this case, the sample space will be like head, tail, tail, okay, tail, head, tail, and so on. Okay. So basically, at each place, I have 2 options. So 2, 2, so 8 possibilities here, right? So there are 8 possible outcomes. If I throw 3 coins simultaneously, this is about simultaneous, right? Okay. So probability is a measure. So probability. So so when I do an experiment, I may define what I'm going to expect from the experiment. Okay. So for instance, if I do an experiment here, so I can define something that I want. Okay. So let's say A obtain a head. Okay. So when I toss a coin, I'm saying I want a head. Okay. So this will be called an event. Okay. So this is my favorable event, like this is something I'm expecting, and then I will ask what is the probability of obtaining an head if I toss a coin. Okay. So if I use a frequentist approach, then obviously we know it's 1 over 2, because in my event the number of elements is 1. So obtaining an head, okay, so it's one possibility here, and then total possibility is 2, so 1 by 2. Okay. So that's how we assign probability. Okay. So so probability, we assign a probability measure PA to an event A. Okay. So we assign some probability measure. So probability measure means like what is the likelihood, right, of that event happening. Okay. Okay. So if PA is close to 0, then it's unlikely. Okay. So that's how we define it. So if PA measure is 0, then it's very unlikely event, and if PA is 1, it's kind of, we scale it like that. Okay. We scale it between 0 and 1. That's the interval. Okay. The measure is going to take. So 1 means like the most likely. Okay. So most likely. So unless it's a deterministic, right, I mean it can take 0 and 1 values. It's an impossible event, then it may take 0 also. Okay. If it's a deterministic case, then it can be exactly 1 also. Okay. Okay. And we recall that probability uses these 3 main axioms. So I just kind of like recall all this axioms of probability. Okay. So I won't do too many examples. I will just recall basic things. Okay. So I'm expecting just 2 classes on prop and stat, and then I will go into the material. Okay. So 2 or at most 3. Okay. So let's see. So axioms of probability here. Axiom 1 says for any event A, so what do we have? Like non-zero. Okay. As I said, I set it between 0 and 1, so obviously PA is like greater than or equal to 0, so that's the lower bound. And axiom 2, all right, so axiom 2 is the sample space probability is 1. So essentially what it's saying is that nothing is left out in your sample space. Okay. So you have all possibilities, all possible outcomes in hand. Okay. So probability of sample space must be 1. So probability of sample space, so let us say we denote we use S for sample space, then probability of sample space is 1. Okay. And the third axiom is if A1 A2 ... let's say so let us keep it ... Okay. So A1, A2 and so on are disjoint events. So disjoint means like, as I said, they don't intersect. Okay, the intersection is empty. So I have two events A and B. A and B are disjoint if A intersection B is empty. Okay, so here we say it like pairwise they are disjoint. Okay, if they are disjoint, if these are disjoint, then probability of A1 union A2 union dot 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 is just the sum. I mean, by pairwise I mean it's like even the tuples A1 intersection A2, A2 intersection A3, but also A1 intersection A2 intersection A3. So all those are like empty. Okay, so it's like non-intersecting. So hence those, by the inclusion exclusion principle we know this, there are negative of A1 union B intersection B or A1 intersection A2, and then there is like subtraction, then again addition and things like that. Okay, so but all those terms will be 0 because pairwise or with 3 or 4 all don't intersect. Okay, so hence only some terms will be remaining. So P of A K plus dot dot dot. Okay, so basically dot 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 means like it's okay as long as it's countable. It's countable because I can have this indexing 1 to k, so essentially it's countable. So countable union of disjoint sets. Okay, I can write in general the union, probability of the union will be probability of the individual events. Okay, so so just focus on the main ideas. So let us. So we know probability now. Okay, so like probability consists of a random experiment. A random experiment we get some outcomes. All collection of those outcomes is put in a sample space. Okay, and we set some desirable outcome. We call it an event, and then we usually measure the possibility of that outcome by using PA, and the possibilities are between 0 and 1. Okay, and few of the results that I won't prove, but you can prove using the axioms of probability that these things are verified. So for any event, probability of A complement is 1 minus probability of A. These are the results we will use. Okay, but you can prove it. Just you need only axioms of probability. Okay, so you don't need anything more. For probability of an empty set is obviously 0. Of empty set is 0. So empty set is denoted by phi, and this will be 0. Okay, and for any event A, as we said, the bounds are between 0 and 1, right? So it's evident that probability of A is less than or equal to 1. I mean, it's evident from the axioms, so you still have to prove this. In the axioms, yeah, I didn't explicitly say it lies within the bound, but you have to use the fact that A is a subset of the sample space. Probability of the sample space is 1. So from here you can say that probability of A must be less than or equal to 1. So these are the tricks you have to use to prove these results. Okay, so and probability of A minus B is probability of A. So this you take it as an exercise. Okay, probability of A intersection B. These are most of the things most of you have done these things just for practice. So probability of A union B is probability of A plus probability of B minus probability of A intersection B, and F probability A subset B. In fact, the fact that I use probability A less than or equal to this itself can be independently proved. Okay, so this is this result. If A subset B, then from the axioms only. Okay, so you try this. It's good to know these things. Okay, and proof, either you prove it or you leave it, it doesn't matter, but just remember this maybe. Okay, so I will give you the reference where you can find these proofs. Okay, so let us see an example of finding probabilities. Okay, I know that for many of you it's repetitive, but let us recall few things. Okay, so you roll a fair die, and what is the probability of the event? So this is a die. Okay, so we are expecting some numbers between 1 and 6, and so in this case my favorable event, I say, let's say 1 comma 5. Okay, yeah, 1 comma 5. So remember, although if I roll a fair die, the outcome is only 1, but what I am saying in my favorable event, I want 1 or 5. Okay, so I'm happy with 1, or I'm also happy with 5. I know that the outcome is only 1, but if you give me 1 or 5, I'm happy. Okay, either way. Okay, so it's possible that event can have multiple things in the list, although the outcome of an experiment can be only 1. It's fine. Okay, it's just that our probability will kind of increase because we are giving more options here. So if so the probability in this case will be kind of like the so in this case it's a fair die. Okay, so since it's a fair die, the probability of each of these, okay, so it's unbiased die, so probability of each of these outcomes will be equal. Okay, so since fair die, probability of 1, probability of 2, dot, probability of 6 are all equal. Sample space probability is 1. Okay, it's kind of like I'm deriving. I know that you know the formula that it's 2 over 6, 1 over 3 probability. Okay, but kind of like we are touching a little bit of the axioms and trying to see, give some reasoning behind probability. Okay, so in this case, fair die implies PIs are equal, and sample space axiom 2 tells me that the probability of the sample space is 1. So the sum of the probability of A1 union A2 union and so on. So in this case, probability of getting 1, probability of getting 2, so on. So if I take a union, it will be kind of sum of these. Okay, so because events 1 and 2 and 3 up to 6 are disjoint. Okay, so I cannot have roll a die. I can have only one outcome, right? So event of getting 1 is disjoint from event of getting 2 and so on. Okay, so we are using this fact. So events, so let us say events are always as sets. Okay, so say 1, 2, in this case 6 are disjoint events. So from axioms of probability, we can use the third axiom, which says that the probability of the union will be sum of the probabilities of each. Okay, so from axiom 3, probability of sample space is 1, and in this case the probability of sample space is essentially the union of 1, 2, 6 and so on. Okay, so let me write that as well, union okay. The sample space is indeed all collection of all the union of all the possible events I have. Okay, and third axiom of probability will apply here because these are disjoints. So this is sum of 1 plus 2 plus dot dot plus 6. Okay, that's 1, but yeah, I mean all these are equal. Okay, because PIs P1, P2, P3 are equal. So this will be like 6 of one of these. So probability of one of these will be 1 over 6. Okay, so okay, so in this case this implies, let's say 6 times P1 is 1. So this implies probability that 1 equals probability that 6 equals is 1 over 6. And since 1 and 5 are independent, I can enforce axiom 3, and axiom 3 again tells me that probability of the event E is probability of 1 union probability of 5. 1 and 5 independent. Axiom 3 implies sum of these, so probability of 1 plus probability of 5. This probability of each of these 1 up to 6 we have calculated is 1 over 6 plus 1 over 6. So this is 2 over 6, which is 1 over 3. Okay, so we did this just to see kind of how we can use axioms of probability, but essentially it boils down that everything we build on will be in the hindsight based on axioms. Okay, so yeah, I mean nothing unusual will happen. Okay. Okay, so from here what we understand is that if it is a fair die, then the rule to calculate probability of an event is essentially cardinality of E divided by the cardinality of the sample space S. Okay, so from here we learn that that for a fair die formula can be used directly. Okay, so cardinality of E by cardinality of S. Okay. So now we when we go to probability, we have like some branches here, like maybe 3 branches, let's say. So probability models. So here we can think of like 2 broad branches, discrete and continuous, and actually there is another branch called mixed. So this is like discrete plus continuous. So it's a mix of discrete plus continuous, like for certain values takes discrete values, but then for certain values it takes continuous values, then from here maybe something like that. Okay, so so there is a possibility to also use mixed. So let us focus on the discrete case. In fact, what we did is discrete. Okay, so let us do some examples on discrete. So when do we define a discrete probability model? Okay, so let us define that. So if the basically everything depends on the sample space. So sample space is discrete and countable and so on. Okay, so if S is countable, if sample space is countable, so countable includes like finite also. Okay, is countable set, then we call it a discrete probability model. Okay, so in this case, in the discrete probability model, in the sample space we can list out elements with indexing 1, 2, 3 like that, and that's the meaning of countability. If I can index a set of outcomes, as 1, 2, 3, in other words, I create a 1-to-1 mapping, 1-to-1 and onto mapping from the set of natural numbers, then it's called countable, right? So 1-to-1 mapping for natural number essentially means I can index. So that's discrete. Okay, if the set of outcomes are like that, you call it discrete. If you cannot write like this, then it's either one of these. Okay, so we will go step by step. Okay, no need to kind of like jump everything. So in discrete space, we would like to maybe study some templates like distributions. Okay, I call distributions as templates because in general there could be many type of problem, but then there are broad categories. We can put them into something is going in binomial, something is going in Bernoulli, something is going in Poisson, and so on. Okay, so discrete we know. Now let us see. Yeah, I mean the example also we know. So for the discrete case, like it's the same thing as we have seen before, but it's just like recalling this again. Okay, so probability of if A is a subset of a discrete sample space, okay, S is some countable, then probability of A can be written as probability of union of Sj, okay, and yeah, so union Sj in A. Okay, so this is same thing as like probability of Sj. Okay, so we are expecting these events Sj to be disjoint. Okay, so I mean there should be some, right? Oh, sorry. Yeah, so we are expecting them to disjoint. So again, it's just what we have seen already. Is just like writing this in a more generic way. The generic thing here is that now S is some countable thing. It may not be finite. Okay, so countable not necessarily finite. Okay, so countable can be infinite. But the fact it's a discrete because it may be infinite, but at least I can count. Okay. So in general, as I said, we can write the formula. So like finite. So in the case of getting an event 1, 5 that we saw before, 1, 5, and what we found out is like the rule is like number of outcomes in the event and the sample space, right? But here it won't work, right? Here, I mean, it's infinite, right? S itself is like cardinality of S is infinite. Okay, so writing in that way may not work here. Okay, but still, like we will have some examples where we can use it in a partial way, but not necessarily that way, because it will always be 0 in that case, right? So okay, or in the worst case, it's like some even numbers divided by the set of natural numbers. Both are cardinality infinite and so on. Okay, so we will see an example where these cases arise, and we don't necessarily have to get into this trouble. Okay. So that's why for this to be useful, I will use finite. In the finite case, this formula is useful. Okay, so finite sample spaces with equally likely outcomes. Okay, so in this case, S is our sample space, which is finite, so there will be some n where it stops, and P of Si, since it's equally likely, so each Si probability is same as Sj. Okay, so in that case, yeah, so in that case, probability, so let A be any event, okay, then in that case we will write this formula explicitly now. Okay, so in this case it will be PA will be cardinality of A divided by cardinality of S. Okay, finite case equally likely, that's the formula. Infinite case, you don't necessarily have to do this, because it reduces to something where on a subset it can be used where it makes sense. Okay, so that's the main thing here. Okay, so let us now go to continuous probability models. Okay, so this is the basic idea about discrete. So now let us define continuous. Okay, and then I will go to discrete, define some probability distributions, and then for continuous as well, PDF, CDF, joint, continuous, conditional, all those things will come. Okay, so then we go into continuous probability models. So in continuous, as I said, the characterization is based on the sample space. If the sample space is discrete, at most countable, it could be finite also, is discrete, and in continuous case, I will say if the sample space is not discrete, meaning continuous. Okay, so if the sample space is continuous, okay, continuous in the sense like it's some interval. Okay, so example, S is some interval 0, 1. Okay, so then it's a continuous sample space. The ideas that you use for the discrete does not necessarily work here. Okay, so I can say, okay, what is the probability? I mean, doesn't work in the sense like it doesn't make sense. So what is the probability of picking a 5 in the interval 4 and 10? Probability is always 0 if I use this, right? So in my event I have 5 and like, so it's 1, and then sample space I have infinitely many numbers between 4 and 10. Okay, so if I go via the discrete probability model, then it's 1 by infinitely many numbers in the sample space. So it's always going to be 0. Okay, so there will be a problem in using this formula for probability measure of an event in the continuous case. It will always be 0 and it won't make sense. So hence in probability, people, when they start probability, they start with something called measure theory actually. Okay, and measure theory is a way to know whether things have non-zero measure basically. Okay, so the problem that is happening here is that we are in a continuous model, but our event has 0 measure. Okay, then you can define a little bit rigorously what measure means. What is something I can measure? Okay, I mean I can measure everything, but the point is like, is it 0 or non-zero measure? Okay, so in this case it turns out that every time it's 0. Okay, a point on a line has a measure 0. A line in a plane has measure 0. Okay, because in a plane I am thinking about areas. If I am thinking of a volume, then plane has measure 0 there, because in the volume scenario I am looking for some volume still to make sense. Okay, so these are the things. So if you study probability theory in maths class, they will start from measure theory. Okay, and when you do integrals also, you will kind of go into a more rigorous way, because if I have to do integral, then integral over what, right? So integral is about finding areas below the curve. Now if you give me set of discrete points, there is no area below that. Okay, because it's measure 0. So if you just give me these 3 points and you ask me to find an area, I will say 0. Why? Because my domain points had measure 0. But the moment you give me some non-zero measure, the moment you give me even very small one, I immediately tell you, okay, there is some area. Okay, I say, okay, this is your area. Okay, now there is a measure, and it happened because my domain has some non-zero measure that allowed me to compute some area. Now if I do a integral of a 3D function, again I will look for an area. I mean in this case it was interval, right? So if I'm doing a 3D integral, then I'm looking for area, like this, over which I can compute the volume. Okay, so again if I do 3D integral or 2D integral, then I need to have some area over which, on my domain, over which I can do. So same thing applies with probability, because probability will at some point involve integrals. Okay, so the concept of measure is important, but we will understand this in a intuitive way. Okay, so I will just tell you, okay, the reason why things are not working is because your measure of your event set is 0. So it won't make sense basically. Okay, but the moment I put a non-zero measure here, so I will say, okay, now you compute, give me the probability of 5, number lying between 5 and 5.5. Now you can use that in the sense of area or the length, not still in terms of number. The idea changes now. Now the probability of a number lying between this is a measure of the length of this. So this is like 5.5 minus 5, 0.5, and divided by, so we have to do some calculation here. So 5 minus 4 is 1, so length of this guy is 1, and plus 10 minus 5.5 is 4.5, so it's like total is 5.5. Okay, so this is what you will report as a probability. Okay, so in discrete, count matters, and in continuous case, measure is important. As I said, if things change to 2D, then even interval will not make sense. Okay, so if someone is asking me like this is my domain, and over which I have to compute like the probability. So I mean that happens in the integral, but here it's like a domain, and then I am asking what is the probability that something lies here. That makes sense because I will take an area of this divided by area of the full thing, so that will be the likelihood of point lying here. Okay, probability of that. But if I again make the relative to 2D, if I just consider lines, doesn't work. Okay, you cannot say the length I will take and then I will divide by the area. Doesn't work. Okay, so if I say what is the probability that point lies here, you will say I will take a length divide by the area. That's wrong. You need some measure in terms of this area. Now here we have the length, here we have area. If I go to 3D, I need a volume. So these are the things we have to be careful about when we are going into 2D and so on. So that's why they study measure theory, because in measure theory the whole idea is about what is measurable and what is not. Okay, so like you can kind of like generalize the idea of what seems to be measurable and what is not. Like I'm not going to the detail of all those things, but there are like big books on just on measure theory only. Okay, these are fundamental questions like what is something, I mean what is meant by infinity, what is countable, okay, like what is uncountable, okay, and what is the concept of a measure. So all this is like fundamental maths questions. So we don't go there, but we just from our practical point of view, we know that when we go into the continuous case, these are the things we face. Okay, so so I will give you some simple examples, I mean exercises, so that we don't spend too much time on the basic stuff. Yeah, most of you can do this. You only need to know some basic thing. Okay, so okay, so let's see what are the let us do conditional probability. You are free to ask questions in the class. We can edit the video. This is video recorded. We can edit the video if you want. Okay, but take it as a normal class. Don't be in a don't take it as like too serious or whatever. Okay, we can do post editing. I mean video is like secondary. Okay, the most important thing for us is the class. Okay, okay, so conditional probability. Okay, so as the name suggests, conditional probability is like I will be given some condition, okay, and then I will be asked to compute some probability. But something will be given to me as a priori, and then the probability might change given that I know something. Okay, so maybe like I can write down some examples for you. Yeah, so let us see this with an example. That will be good enough. So I roll a die, a fair die. Usually it's like always fair die. Okay, so let A be the event that outcome is an odd number, then A is this. Okay, so if I roll a fair die, then outcome is odd, then obviously A is 1, 3, 5, and also B, let us say B is the event that outcome is less than or equal to 3. So in other words, B will be 1, 2, 3, because 3 is also included. Then what is the probability of A and what is the probability of A given B? So the questions are what is the probability of A and what is the probability of A given B. Okay, so this A given B, we call it conditional probability. So it's like you are asking what is the probability of A given that B has happened. Okay, or B is like given. Okay, so if given the, so B has happened means like B happened means like okay 1 2 3 are the outcomes I have seen now. On top of that, I'm asking which of these are odd. Okay, so B given means like outcome are surely less than or equal to 3, and out of these A means which of these are odd. Okay, so what is the probability here, right? So this is what conditional probability means, right? Okay, so so probability of A, if I write down, so we will use this formula, right? So number of elements in the event A divided by the sample space. Sample space is 6, is a fair die, right? So this is cardinality of A divided by cardinality of S, because it's a discrete probability. So this is 1 3 5 cardinality of this set divided by the cardinality of the sample space, which is 6. So in this case we have already seen this is 2 over 6, which is 1 over 3, and probability of A given B. So the problem in conditional, what will happen is the moment B happens, your kind of sample space reduces, because you are given B, so then your sample space reduces. Okay, and then in that I'm asking which of these is odd. Okay, so hence in that case the probability will change. Okay, so so the outcome in this case, let me write on the text. So outcome so the outcome must be among as I said among B, right? So B, which is 1 2 3 less than or equal to 3. Okay, so for A also to happen in the outcome, we must have A intersection B. Okay, so essentially we are deriving the formula also. So now that we are given that B must be outcome must be one of those B, and on top of that I'm asking A can happen or not, then I'm asking A should happen and B has happened, so A intersection B. Okay, so then we have the possible outcomes that we have. So for A to also happen, the outcome must be, it's like intuitively we are also deriving the formula. Outcome must be, the formula was A intersection B divided by B, right? So that's the formula we are trying to derive, right? So for A to also to happen, the outcome must be A intersection B. Okay, and A intersection B is happening over B. The B is now a reduced sample space. So the formula is now very clear, right? So probability of A given B, probability of A intersection B divided by probability of B. So in conditional probability, whenever this is given, this becomes your reduced sample space. That's the main thing to notice. And then since A has to happen after B, they must intersect, like A and B should happen, right? So that's how this formula reduces to this. Okay, so conditional probability, we know the formula now, and in this formula there is a restriction that like this should not be 0. Okay, so we are kind of like, because dividing by 0 is not defined, so we are kind of have an additional assumption that B must be greater than 0. Okay, then we can write down chain rule of conditional probability. So chain rule of conditional probability. So chain rule of conditional probability says that probability of I mean from here we can write probability of A intersection B, which is where the denominator gets multiplied to probability of A given B. Okay, so we write this as a first step. So A intersection B is probability of A given B, probability of A times probability of A given B, or yeah, it could also be B given A and so on. Okay, probability of A given B. I mean either way it's possible, that's what we are trying to say. Okay, because I could have written B given A also. Okay, so probability of B given A is probability of B intersection A is same as A intersection B, because that's symmetric, and probability of A. So kind of I write this as equal to this times this, and from here I write this as this times this. So that's what we have written here. Okay, so essentially this itself gives me some other kind of formula. If I'm given A given B, I can find B given A. So depending on what I have in hand, I can solve for one of these. Okay, given other three are known to me. So it may happen that I'm asked to solve probability of B given A, then I will use this formula. So probability of A given B, probability of B divided by probability of A. Okay. So depending on what I'm supposed to solve, sometimes I may be asked this, then I will solve for this from here. Okay. Okay. So essentially the idea is to kind of like make it as a chain. Okay, so in this case we did it for 2, but then we can generalize this further. Okay, so in general I can write probability of A1 intersection A2 dot 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 intersection of A n, and this is probability of A1 and probability of A2 given A1 and probability of A3 given A2 comma A1 and so on. And so one could essentially prove this, but just keep in mind that there's something like this exists. Okay, but I mean we won't be able to prove everything. We are just doing a review, but it's not required. It's just like we know that okay, there is something called chain rule of conditional probability, and that can be used at later stage. Okay. Okay. Then there is a concept of independence. Okay, so let me define that. So independence. So two events A and B are independent. Two events A and B are independent if probability of A intersection B is product. So we can generalize this to like multiple intersections, and then there will be multiple products and so on. Okay, so this is how we define independence, and if that is the case, then from this formula we can know what this may imply. A intersection B is probability A times probability B, so A gets cancelled. So probability B given A just becomes B. So this means like A kind of had no role. Okay, I was given A, but it didn't affect the probability, didn't reduce the sample space on which the B depends. So that's what independence means. So from here, this implies probability of A given B or B given A. So probability of B given A is just probability. So if I have to expand this, so since A and B are independent, then probability of A intersection B is probability of A, probability of B by probability of A here is cancelled. So this is probability of B, and similarly we can say about the other way, probability of A given B is just probability of A. Okay, so independence essentially means that the fact that A has happened does not affect probability of B, or probability of B has happened does not affect. So this essentially means, yeah, I mean B did not reduce the sample space on which A was being expected. Okay, so that's what independence means. Otherwise B would have reduced the sample space for A, and then it would not have been just the A. Okay, so okay, so that's about independence. So as a small example of independence, independence plays a kind of a crucial role because at some point we consider something called IIDs, and IIDs like independent and identically distributed. So these independence assumptions is quite common, okay, so to say. Like even like things like central limit theorem and so on, they assume independence, IID, okay. So in general we expect that when we are collecting data in a large population, we expect independence, okay, in general, okay. So that's sometimes okay, I mean it's not a problem, okay. So so let us see an example. So here I toss a coin until I observe first tail, okay. So toss a coin until we get tail, first tail, and let x be the number of coin tosses then find probability that x is 5, okay. So here we need the concept of independence here, okay. So what is the independence here, right? So x is the number of coin tosses, and what I am saying is what is the probability that after the 5th coin toss, because x is the number of coin tosses, what is the probability that after 5th coin toss I will get the first tail, okay. So the problem is I will keep tossing a coin until I get a first tail, but then I am saying in how many tosses, okay. So what if my favorable event is like, let's say 5 tosses, okay. So what is the probability that I will get first tail in 5 tosses, okay. So the problem is like this, okay. So what is the independence here, right? So I am tossing a coin, okay, and then I'm repeatedly tossing a coin, okay. So the first coin and then the second coin and so on, okay. So the independence here is that the first coin, the outcomes of head and tail, it has nothing to do with the second time I'm going to toss the coin. So that's the independence, because second time that I'm going to toss a coin, it has its own sample space. I mean it is not doing anything, it's not reducing my sample space in the first case, okay. So the independence here is like each of the successive tosses, okay. I can call it the first toss as event 1, second toss as event 2 and so on. So they are independent, okay. So in this case what we are expecting, so what we are trying to say is x is 5, right. So what I am saying is like on the fifth toss I get the first tail, okay. So the event here means that it has to be necessarily head, because I want exactly at the fifth toss to be tail, the first tail. So this necessarily means that all the previous one must have been head, and then I get the tail at the fifth toss. So this is what we are expecting as an event, okay. And these are independent. So when I write just like this, sometimes I don't write intersection, okay, but that implicitly means there is a intersection. Like I can also, because events are always in curly braces, so more technical way to do this is like this, but it's understood, okay. So probability of h and then tail, okay, in the fifth, exactly at the fifth, okay. I did not say less than equal to 5. If I said less than equal to 5, then the story is different. Here I am saying exactly at the fifth I should get the first tail. This is the exact scenario I have, okay. So here, and since they are independent, so ph, so this is a product, right. Independent means intersection is the product. So in this case it's the product of all 5, okay. So probability of head, probability of head, probability of another head, and probability of tail. And individual probabilities I know. If I toss a coin, what is the probability of h? It's half, 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 and half again, okay. So this will be half, 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 and half. So this is 1 over 2 to the 5, okay, which would be 32, right? Okay, so so this is where we applied independence, okay, where the joint, right, of all these events, because it's an intersection, so we call it joint, okay. So joint of happening this, all this is product of individual probabilities, okay. So that's a good thing about independence, and it's kind of natural in many practical cases. So and it simplifies things a lot, okay. So maybe I have another 5-6 minutes, let's see. So we have talked about joint, and we have talked about, I mean, disjoint events. So A intersection B is empty. So what is the difference or similarity between two events being joint and independent, right? So disjoint and independence. Okay, this may be a little bit tricky. So disjoint does not necessarily imply independence. Independence does not necessarily imply disjoint. In fact, one happening necessarily does not imply other, unless there is a boundary case when A and B are 0 and so on, okay. So one should not get confused with these two facts. In fact, one of them happening necessarily does not imply that. If this is happens, necessarily it does not imply that. Only in exceptional case when so we can derive this from this formula, right? So disjoint means this is 0, okay, because A intersection B is empty, probability of an empty set is 0, okay. So and in the independence case, we are asking for probability of A intersection B is the product of A times product of B, okay. So so disjoint does not necessarily imply independence. So in this case, what we have, so disjoint will necessarily imply empty, and independence means this. Now if two events are disjoint, then this guy is 0. So if A B disjoint, then this necessarily implies this guy is 0. So probability of A, probability of B is 0. This necessarily implies one of them must be 0. Yes, like one of them must be 0, okay, not necessarily both, but this is the implications we have. But this seems to be like a very boundary case. But what this necessarily implies is that if A and B are non-zero, okay, then they cannot be kind of independent as well, okay. So fact that the probability, so this becomes 0, then you cannot have events which with probability all non-zero. So it becomes a very special case. That's what I'm trying to say. So if we are dealing with A and B which probability is non-zero, they don't imply each other at all, okay. 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 Okay, then I can state something called law of total probability, and so yeah, let me do it here. Just state it now, and then we can stop for today. Yeah, I will need maybe 2 more classes to revise probability, and then we can start with the main stuff, okay. So law of total probability. So we can kind of like state it straight away, and then I can explain what it means, okay. So if B1 B2 ... is a partition of sample space S, then for any event A, we have, so this partition is important, okay, and it's also important to recall what is partition, okay. So there is a concrete definition of partition of a set, okay, they should not intersect and their union must be the whole set, okay. So we have, so we can write down, okay, probability of A is sum of I probability of A intersection Bi, and this is, so A intersection Bi, we can use that formula. So this will be probability of A given Bi, probability of Bi, okay, I sum over I. Now this is valid when B is the partition of the sample space, okay. If so, what is a partition, right? So you recall a little bit of, because sometimes you may think of partition as in a yeah, there may be issue there, okay. So let's say I have a set S, A, B, 1, capital A, C, something like that. So give me a partition of this set S, okay. So partition is a subsets of S, pairwise they are disjoint, and union is the whole set, okay. So a possible partition for this is A, a set can have many types of partitions. So another partition could be okay, and not necessarily that it has to be 3. Partition can be in many different ways. So as I said, 1, A, and B, okay. So partition means that intersection is empty and union is the whole set. Intersection is empty and union is the whole set. So if you are given a sample space and if you have a good partition, okay, so the places where this will help you is when you have good partition of your sample space, okay. So BIs will be important here, because BIs, if they are nice, then in that case I will know, okay, I know what is A given Bi and Bi, okay. So partitions are kind of important. Sometimes these partitions will come in the form of a tree, okay, decision tree kind of thing. So this gives you certain partition, this gives you certain partition, okay. So heads I do something, tails I do something, and then some probability calculations are needed at some point, okay. So in that case I may have some clear partition, okay, where what these BIs could be, okay. So say something called choice tree, I will kind of give you some examples later on, and it is in many cases is very natural to use those interesting partitions, and that simplifies our probability calculations, okay. So here this is called law of total probability. Important thing is that BI should be partition of a sample space, and the reason why is that because nothing should be left out from A, because if I am doing a sum over this and I am intersecting with the BIs union of these is the sample space, so I am not leaving out anything, okay. And BIs does not have repetitive elements because they don't intersect, so I am not doing some double calculations here as well. That's like intuitive way to understand things here. So so this is also kind of like important to remember how to do law of total probability. How to I mean, we will see some examples. I think in this case using some examples is important, so we will do this in the next class, okay. So I will take 2 more. It may be repetitive, but that's how I plan to, because even if you have done something, it's always good to repeat a little bit, okay. Okay then, thanks a lot, okay.